for folks for sharing information and results from the last season's monitoring in the Upper Sacramento, and that you're able to spend some of, hopefully, a good portion of your Friday morning with us. Particularly right now, I just want to acknowledge there's just so much uncertainty. So I do really appreciate everyone making time to be here, especially federal agency staff. I know, thank you for everything that you're doing. We appreciate it, and thank you for being here. We're not going to do a full roll call or introductions or anything, but feel free to reference that participant list to see everyone who's here on the line. I know there's a number of familiar faces here, so it's nice to see you all. For those who might be new to the Sacramento River Science Partnership or the SRSP, I'll just give a little bit of some context and some background. So my name is Mary Beth Day. I am with Kearns and West. I'm part of the facilitation team for the SRSP. The SRSP is a voluntary science collaborative. We're focused on sharing science related to the Upper Sacramento River. Our members include CDFW, DWR, NIMS Reclamation, Sacramento River Settlement Contractors, the Southwest Fisheries Science Center, and U.S. Fish and Wildlife Service. The SRSP hosts annual science workshops, as well as today's event, the annual Fish Trends webinar, to highlight key updates and outcomes from last year's monitoring, as well as some other timely science updates from the folks working in this corner of the world. In the past, this meeting has focused mostly on winter run, but over the last few years, we've kind of, and then, acknowledging that for better or for worse, there's a lot of other work and important updates to share across the different runs. So we're now covering some updates from fall run as well as spring run, in addition to winter run this morning. So with that, I will go through our agenda here for today. I have a little bit more, some housekeeping items to cover for a couple more minutes, but then I'll be turning things over to Doug Killen from CDFW, one of our recurring presenters at this meeting. So he's going to talk about last year's winter run carcass and red surveys. And then Tyler McCraney will be joining Bill Poitras to talk about rotary screw traps results from last year at Red Bluff. And then Scott Blankenship is back to talk about some winter run genetic analyses. We're then scheduled to take a break sometime around 10:25, and then we will come back for our second half of the meeting here. So Cyril Michelle with the Southwest Fisheries Science Center will be talking about some smolt mortality hotspots on the Sacramento River. And then we'll move into spring run updates from Ryan Revnick and Mike Mamea with CDFW, and then wrap things up with some fall run updates with Colby House from CDFW, and then Brad Cavallo with Kramer Fish Sciences, rounding things out for this morning. A couple of logistical things really quickly. I know we're all pretty familiar with how this all works at the moment. If you do have any technical issues, you can reach out to my colleague, Bethany Taylor, in the chat or via email. So the way that this will work, we have time. We should have at least a few minutes for questions after each presentation. So we will pause for questions. If you do have a question, you can use the raise hand button, which should be at the top of your screen, or you can feel free to use the chat for comments and questions, and we'll kind of do our best to incorporate those into the flow. Just avoid having full on side conversations in the chat. I'm going to be pretty strict with timekeeping today, just to make sure that all of our presenters have time. But if we do have any extra time at the end of the meeting, I'll certainly open the floor up for any questions on any of the presentations that folks want to kind of revisit today. And then, of course, please stay on mute to avoid any background noise unless you're asking questions or making a comment here. All pretty straightforward stuff. Okay. The last thing that I'm going to cover before I turn things over to Doug to kick us off in just a moment, just some kind of guidelines for today's meeting and honoring the agenda and making sure that I'll be, again, working to manage time and keep everything going. So that'll be primarily my job here today. Hope that everyone is able to be curious this morning and really listening and hearing what updates there are. and just asking that folks are, of course, respectful and courteous. I know there's a lot going on at the moment, but hopefully this will just be a good opportunity for everyone to hear some good updates and learn about what all has been happening. Okay, I think with that, Doug, I think we're ready for you. So I'm going to turn things your way, and thank you so much for presenting with us this morning.
Okay, thanks, Mary Beth. Can everyone hear me okay?
Sounds good.
All right, I'm going to go off camera, but leave the mic on and share my screen. Let's hope it works. That one. And that one.
All right, looks good, Doug.
Looks good. Okay, I'm here today to talk about the winter run Chinook salmon in the Upper Sac in 2024, discussing the adult, primarily the carcass and red survey methods, analysis, and results. Again, I work for California Department of Fish and Wildlife here in the Red Bluff office. A little bit of brief history on winter run Chinook. They originally existed only in the Upper Sac system that included the Little Sac, the Fall, the Pit, the McLeod, and Battle Creek. They require cold, clean, fresh water over the summer months. They only exist in this area, nowhere else. They're genetically unique. Livingston Stone was a federal biologist in the 1800s who developed a Bayard hatchery on the McLeod River, and eggs from this hatchery were sent around the world in an effort to spread Chinook everywhere, it seemed like. They currently only occur in the Sacramento River watershed below Keswick Dam, except for the efforts to move them above Shasta over the last few years. Shasta Dam blocks all access to winter run habitat upstream. Winter run spawners downstream of Keswick were first noted in May of 1945 after completion of the dam, where the cool tail race water substituted for headwater springs, transferring habitat upstream of Shasta to the Redding area downstream. They were listed as endangered in 1989 as drought, pollution, water diversions, and fishing pressure impacted their survival. This is an example of better times if you were an angler. This is an Outdoor Life article from March of 1970, presenting how wonderful the fishing was in March this month now in the Balls Ferry area. That's a picture of the fishing effort in the lower right corner of anglers targeting winter run salmon. So times were better back then, it seems, for fishermen. The monitoring of winter run adults. There was no long-term monitoring prior to the 40 years of the Red Bluff Diversion Dam seen here in this picture. That was from 1967 when the dam was built to 2008 when it was officially removed, or gates up status pretty much year round. There was 3 years of effort on a segregation weir in Balls Ferry. After the dam was built, they were trying to move fish around, so they were counting fish at 3 picket weirs set up in the river, but they got washed out every year, so they discontinued that effort. Carcass surveys began in the 1990s, mid 1990s, and became official for winter run in 2001, supplementing or surpassing the Red Bluff Diversion Dam estimate. Current years from 2003 through 2025, we use boat-based carcass surveys that begin in late April, early May, and run into September. Helicopter surveys count salmon reds, occur weekly, generally from May to August. Keswick Trap removes adults for Livingston Stone National Fish Hatchery from February through June. Red dewatering monitoring begins in June and goes into November. This began in 2013. And the Calusa Basin drain monitoring now regularly occurs on salmon straying into the irrigation canals, especially on years like this one where water is everywhere down there. Aerial red surveys are used to determine the extent and timing of spawning in the river. The proportion of reds outside of the carcass survey, if any, is used to expand the carcass survey numbers. Red location and timing also inform water temperature management actions. This is a picture of aerial flight counting reds. Some of these reds have fish on them. If you zoom in, you can see them. This is a picture just below Balls or a Bonneview Bridge in the Redding area. The aerial red data is put into is available to the public and put into Excel spreadsheets that I post to calfish.org during the winter run season and in annual reports. There's a lot of information on the different runs. In 2024, there were only 26 winter run reds observed over 9 helicopter flights. We weren't able to get many flights during the peak of spawning this year, unfortunately, due to helicopter maintenance issues. Again, the carcass surveys are used to develop the annual population estimate for 4 runs of salmon each year in the Sacramento River. The winter run survey occurs from late April to early September using 2 boats, and we run 7 days per week. It's a collaborative effort between CDFW, U.S. Fish and Wildlife Service, and Pac States Marine Fisheries Commission staff. The crews spear salmon carcasses with long poles and collect samples and data from each fish and return many of them to the river with a numbered jaw tag. Subsequent recaptures of the tagged fish form the basis of the mark recapture methodology used to estimate how many winter run salmon were in the population. Other data is simultaneously collected on the carcasses, such as length, sex, pre-spawn mortality, scales, other biosamples, and coded wire tag information, and others as needed or requested. The results. Carcass survey results create a female in-river estimate. Additional information from Livingston Stone and aerial red surveys are utilized to expand the carcass mark recapture effort. Once combined, as shown in this Excel file, copy of an image, once combined, all sources of winter run data are then used to characterize the population for various management needs and research needs. In 2024, there were an estimated 1,296 winter run salmon in the Sacramento River that returned as adults or jacks for spawning purposes. That 1,296 includes Livingston Stone fish as well as in-river fish. Following the creation of the annual population estimate, the annual data is available in a summary table providing winter run data for categories of interest for various users. Call this the winter run Chinook salmon data table is available for various categories from 1996 to 2024. It's obviously trying to fit all years and all categories of interest on one spreadsheet is difficult, but in this view, you can can't zoom in. Roll the mouse. Nope, there we are. Still can't zoom in, can I? In this table, there's a lot of categories. Most of them are developed by request for people to include data for their own needs, but you can see there's quite a bit of categories. If you're interested in winter run data, this is available online, this table, and you can either request it from me or go online, and it covers all the various years of winter run data that you could ever imagine you need. So let's see. Other winter run data, carcass survey data is combined with data from Livingston Stone National Fish Hatchery to create the annual population estimate. Many of you are familiar with it, but some of you may be new. Shasta Dam is on your right in this photograph. Livingston Stone is underneath the black arrow there. It's at the base of Shasta Dam is a conservation hatchery that uses up to 120 adults, give or take a bunch depending on the year, to produce around 200,000 juveniles, more or less in some years. Adults are captured at the Keswick Dam. Juveniles are released in Reading near the end of January into March of each year. This is a picture of Keswick Dam. It's about 352 miles from the ocean. Okay, good to hear. The fish ladder is at the yellow arrow under those 4 tanks, and it leads to an elevator trap, which is raised up, and the fish are trucked up to Livingston about 20 minutes away. They are sorted and hatchery broodstock fish are selected and tanked until ready for spawning in the summer. The shallow Dewatered red monitoring is another aspect of the winter run monitoring. It occurs in concert with the carcass surveys. This effort monitors winter run red dewatering annually. Dewatered red surveys begin in June for winter run. They're designed to identify any shallow water reds that may become dewatered if flows are lowered later in the year. Depending on water temperature, Chinook reds can take between 70 to 100 plus days for juvenile salmon to emerge from the gravel and start feeding. So we go out, we mark active spawning reds in shallow water in the hopes of preventing dewatering months later in the future, in the future efforts as the fall run starts spawning. Shallow winter run red monitoring was initiated in the 2013-14 season. Physical data includes location, depth, photo, fish presence, etc. On the left, there's a picture of a person, dewatered red staff measuring shallow reds, or in this case, a dewatered red. Now on the right, this year we put up signs at the Redding kayak, canoe, raft launch site there at Posse Grounds by the Convention Center in Redding is a popular launch spot for recreational users. And we encircled the shallow reds and put up signs. We encircled the shallow reds with natural white rocks collected, and you can kind of see our effort to protect people from trampling on the reds by encircling them with the white rocks. And then the signs said to please don't trample the reds. Shallow red efforts in 2024, 17 shallow reds were monitored. One was dewatered before the juveniles had a full opportunity to emerge from that red. In total, there were an estimated 375 winter run Chinook reds in the river this year, and 0.26% of these, one was dewatered. Again, this data is all combined into one winter run file that is updated weekly in CalFish during the season, and then finalized later as the efforts wind down. That's it for me. I'll take any questions if there are any. Further information on winter run data can be found on the website at the following link, or by contacting me at doug.killam@wildlife.ca.gov. Okay, if there's any questions, let me know.
Bill, you're already ready. So I'm going to hand things over to you and Tyler.
All righty. Thank you. I will turn off my camera real quick because we have limited bandwidth up here in Red Bluffs. So I'll come back on a little bit and we'll have Tyler come on when he presents a few slides in this as well. So I'll get started here. I'm going to show and just talk about some of the Red Bluff Diversion Dam Rotor Screw Trap Juvenile Fish Monitoring summary of results here for 2024, which is an interesting year for sure, and good and bad in a lot of ways. So we'll get into that real quick, and I'm going to focus our talk a little bit here on some of the work that we did that really supports some of the research and activities of the science partnership here. Namely, activities number 11, 12, and 13 were worked on in 2024. And we'll get to those in a minute. Along with that, we also did a small acoustic tagging effort of wild Chinook. I'll talk about that real briefly too. This was after the spring pulse flow tagging studies that occurred. So fish numbers were limited, fish tagging was limited, and the results are interesting as well. But either way, we'll talk about that in a second. I do want to point out that we're a little behind in reporting. That's primarily due to losses of staff, short staff in 2024 a little bit, and then recent losses. But I'm hoping to catch up on some of those things, and actually some of the work and activities 11 and 12 that was conducted in 2024 are delaying the progress on those reports because we're doing quite a bit of things differently here. So I'll get into that in a lot of detail here in a second, but hope to get that reporting through November 2024 up by about May or so. So we'll see. Either way, let's get into it. For activity 13, we did collect tissue samples for that work. Scott Blankenship's on, I think, after me. We collected samples for year 8 of the parentage-based analysis from the juveniles, about 1,340 samples. Those were recently transferred to CDFW, the archive there, and then onto him for that analysis. Beyond that, we also took 153 samples to make some genetic-based corrections on our estimates for the winter run, spring run, length of date corrections, we call them, because we get a number of fish that arrive in late October to November. And we found that genetic corrections during that period really help improve the accuracy and precision of our estimates there. So we got a number of those incorporated into the JPE right now. So that's good. But also we collected every single winter run mort that we came across in our sampling and provided those to UC Davis. Rachel Johnson's work with UC Davis nymphs for the otolith work. About 264 of those samples were recently transferred to them for their analysis, and we'll see what happens with those. Anyways, in 2024, we did not work on activity 28, which we've worked on in a number of years, and that was doing some fish health pathogen work. We did support Miles Daniels, who put in a proposal for funding for additional years of work on this, so we'll see what happens there. But none of that was conducted in 2024. Moving along real quickly here, just some real preliminary quick results on some of the acoustic tagging work we did. We did tag 62 natural origin fish in June of 2024, released them at Red Bluff where we caught them. And it was very interesting to see that, of course, we see good survival about 4 or 5 kilometers downstream at Salt Creek here. On the left, 93.5% of those 62 fish made it there. You also notice the flows are pretty high here. We start to see the summer increase in flows out of Shasta and Keswick for irrigation season. You then go down further about 150 river kilometers down to Meridian, and technically the flows here are Wilkins Slough even further down. Flows are much less, about half. Our survival is about 1.6 at this point, to that point. We've seen this the last few years when we're doing these releases in June, and we're kind of looking at what appears to be the end of the survival train, if you will, through the Sacramento River, based on acoustics, of course, of fish that are not making it out of the system as temperatures change quite a bit, flows change, and so on and so forth. Quite a bit of change occurs at that time. So we're kind of documenting the end of the successful passage of a lot of fish with some of this work. Anyways, moving on, let's get into the meat and potatoes of this, which is really the rotary trapping project, the juvenile fish monitoring work that we do. 2024 was year 5 of the updated array, we'll call it, with 4 5-foot rotary screw traps and 1 8-foot rotary screw trap. I'll note that sampling effort was moderate through, I'll say, between January 1 and June 30th, which is primarily the fall run out migration period. We did have quite a few high flow events, knocked us out of the river for 22 of 182 days in that period. Staffing limitations also contributed to that. For one, if we don't have full staff, then we can't sample as many days, and or we can't sample as many of these higher flow events because we randomly subsample those events. And if we don't have enough staff, we can't get as many of the pieces of those samples that we normally get. Either way, we also did not sample around a few hatch releases. And that's typical to try not to impact those fish as they move through, typically in March and April. And we lost about 12 days there. Sampling effort was moderately high, I'll say, not as high as last year. It was 91% for the primary winter run out migration period, which is July through December of 2024. We lost about 17 days in that period, 3 for holidays, 1 for the park fire because of air quality issues in the summer. Not a big effort there, but 13 storm conditions days also. Along with that, though, we did attempt to capture more fish during the winter run period by doubling up traps in some of the gates. But even that attempt was not successful in getting us a decent amount of fish to conduct marker capture trials with those fish. So none of that occurred in that period. We did a few last year in the fall run period, though. Either way, these challenges that we had and the effects, again, high flows, as you can see from the hydrograph here on this graphic here, excellent runoff. Great conditions for fish, I would say, not so great for sampling the river. Not the highest flows we've ever seen, but at the same time, a number of events with some pretty good peaks on it that we're unable to sample consistently through. We did have woody debris and safety issues again, less than full staffing through the winter period until about April 7th, at which point I then lost a data manager in April. So that affects our ability to bring up data online and things like that too. But we then had full staff essentially through the end of to the end of 2024, which was great. But overall, some of that results in reports being delayed. Less work was being done at certain times at the early part of the year, like I mentioned. Passage estimates, well, what's the effect there? Well, more imputation for those missed days. There's some moderate fall run impacts on those estimates for sure. I'd say they're relatively minor. Overall, I'd say 2024 was less than optimal sampling year for juvenile fish at Red Bluff. Want to point out a little bit of 2024 data, preliminary data, of course. We sampled through the primary out-migration period. Obviously, that was looking about August through December. We've been a little hit and miss at the end, but haven't seen much. You know, January was, in a sense, very dry. That's 2025, of course. But after a lot of these flow events that we saw, we haven't seen much for winter runs since the late December period and all. Anyways, let me move into trends because this is the fish trends meeting, right? So we want to see some trends in juvenile fish passage at Red Bluff 2024. And again, these are preliminary. And I'll note that 2022 and 23 are being revised with some new modeling efforts that Tyler's going to talk about here in a minute. So these are preliminary numbers, of course, at this point. But 2024 so far, and this is essentially through the end of December, is really looking like not one of the best years in terms of juvenile out migration, but at the same time, it is hopefully going to be better in 2025. We'll see. Moving along, the overall passage of juvenile fish, you know, Red Bluff, we see a lot of our fish before anyone else in the system, and this year was no different. It was interesting to see that those storm events in November, that's when fish were captured lower down in the system at, well, actually they caught quite a few in Sac Trawl during an event, which I don't know if the rotary traps were out of commission at Knight's Landing and Tisdale, but they seem to get the most of their winter run in the January or late December to January period. So that was kind of interesting to see here. So something to check in on that. Otherwise, want to get into some really cool stuff that we did get to work on for a little while here, which coincides with SRSP activities 11 and 12, and quite a bit of statistical methods review and updating. And for this part, I would like to introduce Tyler McCraney, who is no longer with us currently, but we will see with what happens here as far as bringing back employees who were removed because of probationary periods, if he'll be back or not. But either way, wanted to give him an opportunity to talk about some of the exciting things that he's been done that really coincide with work that has been requested by the Science Partnership for our work, and something I've been wanting to do for years. And so, Tyler, why don't you come online and we'll get you started here for the next few slides, and you can talk about what you were able to look at and do.
Hi, thanks, Bill. Hi, everyone. So yeah, I started work at the Red Bluff Fish and Wildlife Office in late October, and really went to work reviewing the statistical methods and the data analysis pipeline. At the core of the rotary screw trap operations and estimation of juvenile passage is the trap efficiency model. And so I dug into this, and I wanted to mention a few things about it. So the method uses a ordinary least squares regression model to predict trap efficiency on day D from percent Q, which is the percent of the water transect sampled by the rotary screw trap fleet. So here I have two brood years, 2022 and 2023, and on top are the legacy models that had been used. So these models were developed during the period of 2018 to 2023, when this was a time of change in the river morphology following the decommission of the dam, drought years, and then a movement of sedimentation and a real change in river morphology. That also led to change in the operations of the rotary screw trap fleet, a change from using 4 8-foot traps to a combination of 5-foot traps and 8-foot traps. So I reanalyzed the raw trap efficiency trial data, and I found a few bugs in the existing process that relating to calculation of percent QD, and also the the efficiency on day D as well. So I reanalyzed that data and I fit new linear models to that using just standard statistical procedures to identify a couple influential observations or outliers that improve the results here. So the new fit is on the bottom panel. And so a couple things. The new fit, it's increased the slope a little bit and it decreased the y-intercept. So there's also rugs on these plots that show the daily values of percent QD during that brood year. So you can see in both brood years that the density of the highest density of observations is within the range of trap efficiency trials, but there's also in both cases, for the legacy models and in both years, there are some observations that are out, being extrapolated from the model. So it'll really be good to get incorporate more trap efficiency trial data into this. However, using an ordinary least squares regression isn't the best way to model trap efficiency, because the trap efficiency is generated by binomial trial data. So OLS regression would be okay if the efficiencies were a lot higher, but when the efficiencies are low like this, it doesn't work very well because they're bounded by 0. Another thing that I found is that the efficiency of traps is not homogeneous across the fleet. So the capture efficiency is a lot lower on the river margins and a lot higher in the central channel of the river, especially when the 8-foot trap is in the center channel. Next slide, please. So to address these issues, I fit binomial generalized linear models to trap efficiency, and doing this in a gate stratified manner. So each gate, they're arranged here from west to east, gate 8, 7, 6, 5 to 1. That's how they're arrayed in the river channel attached to the dam. So for most of these trials, and this is the same data that was just used for the linear models that we were just showing, most of these gates have trial data including both 5-foot traps, the new ones, and 8-foot ones, the ones that were used before the river changed and resulted in a situation where they couldn't be fished properly. So like I mentioned, the efficiency is different on the side channels and in the center channel of the river. You can see the model formula, the coefficients are pretty similar for gates 8 and 1 on the sides. And then they're more similar between 7, 6, and 5 as well, which kind of reflects that. Again, I put rugs on here to show the range of observations that we have from these brood years. And again, the density for many of these is within the range of known trap efficiency trial observations, but there are quite a few observations that are outside the range, and so it'll really be good to include more trials here. Something I also want to mention is that gate 6 doesn't have any trials with a 5-foot array or a 5-foot trap, and then gate 5 doesn't have any trials with an 8-foot trap. So that's something that Bill's working on right now with the crew to get some more trials to add to these. So it's limited by the number of trials we have, but that's something we're hoping to get more of. So to use this gate stratified approach for trap efficiency modeling to estimate passage, I developed a split apply combine strategy to first estimate percent QD of trap I. So that's the percent Q for sample day D on trap I, and then I estimate for each trap the trap efficiency of that individual trap on that day, and then those individual trap efficiencies get summed together to just get a trap efficiency for the day, and that's used to estimate passage. Next slide, please. I've also been working on new methods to generate confidence intervals for passage estimation. I went through the existing workflow that's used to estimate theoretical confidence intervals based on a student t-distribution. I found a few minor bugs in that process that straightened out. They didn't make a huge change in it. Typically, these theoretical confidence intervals are very wide. Here, these are 95% confidence intervals. The top panel shows the theoretical confidence intervals that are generated for winter run. And this is, by week, it's showing them. So, and so I developed some new methods to generate bootstrap confidence intervals. This uses the two-step bootstrap procedure. The first step is that we bootstrap the trap efficiency model in various ways to get an estimate of sampling variance from using the same trap efficiency model. And then the second step is to once that bootstrapped efficiency model is applied to re-estimate passage for those days, and the second step is a bootstrap that samples with the replacement the sample days within the week to get an estimate of sampling variance of that part of the calculation. So as pretty cool results, we thought. We were really excited about this. In general, the bootstrap method is more precise. So you can see that on the top, that's the theoretical confidence intervals, and then below that is a bootstrap confidence interval for the linear model that's using a single model for the entire process of estimation. It's generally more precise, not always, but generally more precise. And then on the bottom, it shows the bootstrap confidence intervals for the new gate stratified general binomial GLM approach that I developed. Next slide, please. So yeah, just to go over a few things. Been working on this new binomial generalized linear model to do gate stratified trap efficiency. Develop some new methods for confidence intervals using a two-step bootstrap algorithm. And these are more precise, and I've completely rewritten the entire process in R code, in R functions. So the pipeline is all done in R. You just enter dates of when starting and ending, when to estimate, when you want to estimate passage. This is the little screenshot right here. One of the first function that queries the Microsoft Access database to pull that data into R. But I developed these functions pretty flexibly. They can incorporate all the legacy trap efficiency models, so you can choose which model that you use. You can choose different approaches for bootstrapping the trap efficiency model. So there's like parametric, semi-parametric, non-parametric methods for that. So it's really fun. I was about 2/3 of the way through with that, and then I got axed. So hopefully I can get this work done, and it's been great working on this. So I'll pass it back to Bill. Thank you.
All right. Thanks, Tyler. Yeah, we'll get into that a little bit more, but yeah, that's the hard part about all this, is that there's a lot of exciting things going on here, and yet they're not complete and they're not essentially functional. And I'll talk about that in a little bit. But I do want to touch on a little bit about that precision. And actually, I'm going to skip on this and just show you a visual graphic. We're talking about that precision, and what ends up happening is those fry equivalent values get put into a simple calculation to do a rather coarse level winter Chinook egg to fry estimate. And what you can see on this figure here is estimated egg to fry survival in percentage on the y-axis here. The red points are the point estimates based on those fry equivalents, and the black points are the confidence interval estimates around that. In low water years, we do a lot better sampling, so our variance is a lot lower. But what you'll see here is that when we start to use this new GLM method, the precision is much better and tighter around those estimates. And so if I toggle back to some of these values, I've only gotten to 2022, 23, and 24. And I should say Tyler has. We hope to go back and change 20 and 21 by using that other method, since that's when we started using the new trapping array. And what you see here is just for an example, look at 2023, the data is saying about 20.68% egg to fry survival with about 2% on either side of it. The older methodology we had been using gave us a different estimate of about 25%, but it's about plus or minus 10% around that estimate. So huge difference in terms of precision. And hopefully this is something that people would be appreciative of, that, you know, our values here actually fall within these values. So I think that we've had some accuracy in what we've been doing, but the precision is much better, and that's where we want to improve our methods here, at least, as well as making sure that now we know areas that we need to sample and run traffic efficiency trials better to, in a sense, get a better model that is representative of what we're actually seeing out there and measuring. And of course, we enter 2025, and as Tyler mentioned, he was he was let go about a month ago, which is unfortunate. So unfortunately, a lot of what we've been doing is kind of on hold. It's very much on hold, actually. So the current status of all the work that he was working on is that it was incomplete, so it is on hold. We don't have people who are able to pick this up and run with it and complete it at this time. We've had quite a bit of loss of probationary employees. Of course, Tyler being the top one here, fish bio data manager, statistician, and excellent coder. A huge hit to the program, of course, but we've also lost 4 field staff. So the project itself has lost 40% of its staff. So we are down quite a bit. The automated data pipeline that we were working to get this information to SACPath so people could query it out as they liked is incomplete. We're unable to provide real-time updates to SACPath right now. Monthly updates of raw data at EDI, that is being done periodically. I actually just got one of those done the other day, so there's a new update on the website through, I think it's February. But that's going to be done periodically because the pipeline for that was not completed either. And of course, the reporting stalled because we've got some new methods to work out and to incorporate into those reports. And we need additional code and write-ups to finish that progress and process. And at this point, we'd also like to get that stuff peer-reviewed to make sure that it is of best scientific quality for this group and others. So with that, if you are looking for data and reports, we do have some things available, not completely up to date, but raw data is available. SACPath has data through the end of 2024. We've got some acoustics data, and as well, we've got a few reports. If you need any other data, then let me know. At this point, we hope to see Tyler back here soon or work through another venue. I know this is a lot of information, and there's a lot more that could be discussed. And if it's of interest to the Science Partnership, we can maybe have another meeting about this topic on its own. But with that, I'm not sure where we are on time, so I'll send it back to Mary Beth, and she can let us know if we have time for questions or discussions. And thank you. Thanks, Tyler, very much for your work.
Let me turn things over to Scott Blankenship with Kramer Fish Sciences. Scott, thank you so much for being back to talk about your genetics work.
Yeah, thank you. Good morning, everybody. Appreciate the opportunity to talk. Let me start the slideshow. Up, ready to go?
Yep, looks good.
So I'm going to be talking about some interim genetic monitoring results. This work got started in earnest during the drought years, but we have a number of years under our belt now, so hopefully we'll get this out in a publication soon. Wanted to start with, let me dismiss that. Wanted to start with some acknowledgements. It takes a village to do a large study like this. There's lots of folks in Kramer Fish Sciences and the genetics group that touch this and are vital to sort of make the technical aspects work and the genetic data available. Funding for this project was largely provided by the Sacramento River Settlement Contractors and the Bureau of Reclamation. And we don't do any of the monitoring, so all of the monitoring is done by the fish agencies and is the sort of the foundation for the material that we use. So groups like Doug Killam's group and Kevin Niemela and Bill Poitras, just to name a few. This Leah at the archive. We rely on all these folks to get the metadata and the information we need for these studies. So thanks for that. Instead of having just a data talk, so I gave this similar talk at the Bay Delta, and it was just sort of mostly data, and that was a little bit unsatisfying. And so for a video conference like this, I thought I would add a little more context at the front end of this to perhaps make it a little more pleasant. So I have a few slides here. I'm going to try to make just a concise sort of statement about these items here, goals, what we're doing and why we're doing it, and then expound on that a little bit for a couple slides, and then go into the results. So the goal here is to demonstrate how genetic methods can enhance existing population monitoring. So we're bolting these methods onto existing programs to add content and value to that. What are we doing? We're using parentage to partition or quantify recruitment. I'll go into that a little more. And why are we doing it? I would say that the spawner abundance surveys and the Fry equivalent estimate surveys are absolutely vital, but they're insufficient for evaluating the effects of directed management actions. So let me go into what we're doing a little bit more. And I've used the same cool slide that that Josh took that Bill had on his presentation. When you're encountering and trapping juveniles coming out of a natal area, it's unclear what factors led to the arrival of the naturally produced juveniles being there. So we don't know where they came from. We don't know what conditions they may have experienced individually. Also, nothing is known about their parents. So were their parents hatchery fish? Were they wild fish? Where did they spawn? When did they spawn? We don't have information about that. Parentage provides a means to gain those insights. So we can tie juveniles through parentage back to parents observed from a previous state. So now we have information about the parents that contributed to those juveniles, when and where they spawned, how big they were, whatever. We also can estimate what environmental conditions those juveniles may have experienced, things like that. So we can add information to existing programs that way by just incorporating parentage information into the mix. For the winter run study here, there's lots of different ways you can configure a parentage study, but for the winter run study here that I'm going to be talking about today, these are the metrics that we're producing from within the study design. Adult abundance, sex ratio, the recruitment rate, or it's really the recovery rate. There's an egg to fry survival that's internally consistent with just the genetics data itself, effective population size, effective proportion of hatchery origin spawners. The differential recruitment is a modeling effort. So what factors or covariates are associated with juveniles being observed versus not being observed. And then obviously genetic diversity metrics of all kinds are available. So if I have time, I'm going to be talking about all these except for genetic diversity. Now on to why we might be doing this. This is just a basic abundance chart. I'm sure everybody's seen trend information on Chinook on the West Coast. This is for winter run, the population itself. For several decades, the winter population has been, bouncing off a low population size. One sees similarities with other Chinook populations as well. There's a lot of interannual variability in abundance, and there's low abundance relative to an earlier time point, right? but data like this aren't particularly informative for the effects of management actions on reproductive success. To increase abundance or increase diversity, which this is my opinion, is in most cases the action's purpose is to increase abundance or diversity. The reproductive success of some individuals out on the landscape has to be improved. That's the mechanism where you're going to get abundance or diversity changes. So higher resolution information is required. An example of that higher resolution information is the winter run study, like I'm presenting here. There's other examples out there. One is a recent publication that we have on the American River Fall Run, where we use a parentage design to get at relative recruitment production from gravel augmented sites versus non-gravel augmentation sites. So it's using parentage to understand the performance or the benefits of habitat restoration, trying to get any information on that at all. There's also a similar concept for steelhead in the San Joaquin Basin, although steelhead are a much different beast, and you don't see adults. Juveniles aren't captured in screw traps, things like that, so it's a little more intensive. But there's work out there trying to explore use of parentage methods to get population information. All right, that's the context. So on to some specifics here about the winter run population. I'm going to show brood years 2020 through 2023. I've talked about earlier years before, so some of you have maybe seen this. We're adding on some information here. Activities from the Science Partnership that this pertains to. 13, that's exploring parentage methods to provide information about reproductive success spawners. 29, routinely develop summary brood year assessments. Those occur, but this can enhance that. And we do provide these data to the folks that are producing that. For the collections, I'm not going to talk about all these slides in hyper detail. People can get these slides later if they want to look at them. Some things to point out. We've increased the numbers of samples from carcasses that we take if they're available, because there is a high failure rate. So, we have a certain goal that we initially started with. That's probably going to be revised at some point, but we had an initial target. But the high failure rate of carcass tissue, we've escalated the sample sizes we have because we have some high failure rates. So, pushing 60, 70% in some years, which is no good. A lot of wasted effort. For 2023, there were only 381 carcasses available, so we actually did sample those in duplicate, which gave us a lower error rate. Failure rate. The numbers in parentheses for these carcass estimates, the genetic data can pull out essentially the ESU, right? Is it a winter run? Is it a spring? Is it a fall? That sort of thing. Though the numbers in parentheses are samples in the winter run survey that aren't winter runs. So that's a non-zero value. This is in a total aside, with the substantial changes that have happened this year on how ESUs are identified, we're going to be able to get some more insight into this. I think I have some ideas about what's going on here, but just for the purposes of this slide, there are, the QA/QC step is to pull out non-winter run from the winter run collections, just so we have a apples to apples comparison. There are obviously many metrics produced by agencies. I'm going to add some metrics that to the bottom of this table that are from the genetic study, but I'm just going to start by listing some of the metrics. And as I saw Bill's presentation previously, the egg to fry survival numbers may be off as they're being revised here with different analytical approaches, but so just bear that in mind. Abundance is on the top there. That's in-river escapement, excluding the broodstock that are removed from the river. The estimates of females present, egg to fry survival. So in 2020, it was about 11%. It dropped down to the 2% range with the challenging water years of 21 and 22. And with the good water year of 23, it went back up to, maybe double the 2020 value. Some of the associated temperature-dependent mortality estimates are shown next. So less than 1% in 2020, shot up pretty high, over 70% 21, and then dropped back down to 0 as we trended towards 2023. First off, from the genetic metrics for estimating abundance, I've showed some of these results before. The 2020 value differed pretty substantially from the official estimate. No way getting around that. Let me switch to another slide here, which shows the confidence intervals around these. Might be a little easier to see. So the confidence intervals overlap in 21 through 2023 for the metrics, and they differ pretty substantially for 21. For the in-river percent female, that's a metric that gets estimated from the marker capture or the close kin marker capture model that's estimating abundance. We use the as a prior, the estimate that is provided by CFW. That percent female does differ, the output from the model, and it doesn't just trend higher or lower. It sort of jumps all over the place. The egg to fry survival, that's just calculated from using the recruitment information of the genetic data set. Was about egg to fry survival was 6% in 2020, went down 50% in the 21 water year. It went down another about 50% in the 22 water year, so it wasn't flat like the egg to fry estimate up here, and then jumped back up to 16% for 23. So somewhat about twice what it was in the 2020 level. So kind of trended with the U.S. fish estimate, but was a little different. On to effective size. The annual estimates of effective size are shown in the 300 to 400 range. You'll notice in 23 the effective size dropped down fairly substantially. The effective population size is a generational measure, so if you do an estimation using all 4 years here, the general measure is right around 300. It's useful to interpret effective size given, say, the 5,500 conservation rule, if anybody remembers that out of antiquity. The 500 range is something that might be approaching a standard for recovery. 50 is where inbreeding kicks in, so that's a real concern. So this metric has been pretty stable as far as I've seen over a long period of time. It's not a recovered state by any means, but it's not a threatening state near term either, in my opinion. It is a concern that 23 dropped down significantly. We're gonna have to explore that a little bit. That's a cause of concern. Might be some insight into that in a few more slides. Recruitment rate. This is essentially a recovery rate, a recruitment rate for hatchery fish displayed in I have that labeled right. So the adipose fin absent fish, those are going to be hatchery origin fish, and the adipose fin present fish are going to be in orange. So you have for whatever reason, you've had a sort of a divergence of fortune in the 2022-2023 range. We haven't gotten into the potential mechanisms for that yet, but we are observing some trends there. This is sort of a wonky slide, but it is a metric that one can provide that is difficult to obtain by other means. The PHOS is a hatchery form metric, so it's the proportion of hatchery origin spawners on the spawning ground. But you can adjust that based on reproductive success. So if relative reproductive success of hatchery and natural fish are the same, that RRS value is 1. So that ratio is 1 if the success is the same. If the recruitment rate is higher for hatchery fish, that value goes up. If the recruitment rate is lower, that value goes down. So you can discount the numbers of hatchery fish on the spawning ground based on their reproductive success, be it good or bad. So that's where the effective PHOS value comes in. And then you can use the effective PHOS in lieu of just a count PHOS to refine that estimate of proportionate natural influence. So for the winter run population, this is typically approaching 1 or 1. Because you're only using natural origin brood stock and things like that. But with the increase in hatchery production for the drought years, that effective PHOS changed, which affected the P&I. It's just metrics to track that can be relevant to some folks depending on what we're doing.
Scott, I'm just going to jump in for 1 second. You've got like 5 or 6 minutes for your slides, and then I want to move to questions if that works.
Gotcha. I'll blow through this awesome. Last bit here. No problem with time.
Thank you.
On to the modeling effort. I'm not going to go through this because it's unpleasant for folks that don't model, and we're running out of time. So just to let you know that recruitment can be used like 1s and 0s, right? If you see a juvenile, it's a 1. If it's not, it's a 0. You can try to model what contributes to observing juveniles versus not observing juveniles. There's lots of values you can use. These are the metrics that we've modeled thus far. Year, fork length, hatchery origin or not, location, temperature dependent mortality, things like that. Sadly, nothing has come out really statistically significant. I was convinced temperature was going to play a role here, given the vastly different temperatures we saw, but it did not. And I will skip over the next bit. I do have one other slide about temperature dependent mortality. So you can see when temperature dependent mortality is 0, it's obviously better. You're getting more recruits per female observed. But for almost any other value of TDM from really low values up to 1, you're seeing recruits. It's almost uniform. So the genetic data could be not detecting this effect at all for whatever reason. The temperature effect could be elsewhere. Also, the temperature model and the incubation model itself could not be functioning quite right. Hard to say. but as of now, TDM is at least uninformative for me for trying to predict recruitment. Just to sum up, carcass tissue quality could be improved. There's some ways around that. We've talked about that, but it has to work for the field folks and make sense for the archives and things like that. Mean abundance estimates did differ by year. The confidence intervals did overlap 21 through 23. Survival decreased and TDM increased over the study period by an order of magnitude. The egg to fry survival and the genetic version of that dropped 50% in unfavorable years relative to more favorable years. The effective population size was right around 300. 23 was notably lower. We need to investigate that a little more, provide some context for people. In-river environmental covariates, temperature, spawning location, did not explain spawning success patterns, and TDM did not explain patterns of spawning success. That's all I got.
All right, thanks, Scott.
Yep.
Thanks for joining back after the break. Today I'm going to talk about Chinook salmon smolt mortality hotspots on the Sacramento River. So just a little background for those who are new. There's been quite a bit of acoustic telemetry work done in the Central Valley and in the Sacramento Basin. We've used different technologies over the years, but we've kind of settled on using JSAT's technology. So it's the Juvenile Salmon Acoustic Telemetry System, developed in the Pacific Northwest. Most researchers in the Central Valley now use the same system of receivers that can detect fish as they move downstream, which allows us to both estimate their migration rates, but also their survival as they make their migration to the ocean. And this technology allows us to tag fish 80 millimeters or bigger. There are some newer tags coming onto the market soon that should allow us to start pushing that size threshold a little lower. But for now, we mostly tag what we'd call smolts or maybe pre-smolts. And so the remainder of this talk is going to be focused on that life stage. And these tags emit unique IDs. And so we can track individual fish as opposed to things like code wire tags, which track large groups of fish. So we've been doing this since about 2007. The early days were more VEMCO focused, if you're familiar with that technology. And since about 2012, we've mostly used JSAT's tags. So this figure here is really just to show how the technology has kind of grown more popular through time, and as the years have gone by, we've had more and more unique studies that have tagged fish. And so each one of these points in each box is an estimate of survival to Benicia Bridge for a study, and the color coding is based off of the population being tagged. So again, not necessarily to focus on the actual data here, but more to demonstrate that we have a lot of information and we're still collecting information at this rate in the 2024 and 2025 years. So, and you know, a lot of these studies have gone to publish their results. And one of the things that these studies tend to report is the reach specific survival. So what's the survival through each reach that the fish swims through on its way out to the ocean? Here's just a few. There's several more I'm missing here that have estimated reach specific survival. But the problem that I personally have had is a lot of these studies are you know, from just a couple or a few years, and also the researchers had to select some receiver sites with between which the reaches get defined, and these are not consistent from study to study or from year to year, and so it's kind of hard to mentally you know, comprehend where in the river we might have exceptionally good survival or poor survival. And I think these figures kind of just show, you know, there's these reaches defined by these different studies are not the same reaches. A lot of these reaches are different reaches. Some don't use the same receiver sites as others. And so these aren't necessarily apples to apples. And I decided that personally, I just wanted to better understand how survival is laid out through the river. So that's kind of the focus of today's talk. And yeah, just to reiterate kind of the problem with why it's hard to synthesize reach-specific survival from this 13-year data set. So one of the reasons is receiver sites do perform poorly in some years. This can be due to things like high flows, which tends to reduce the listening range of a receiver. It can also be due to vandalism or theft. Sometimes receivers are removed from the raw water or destroyed. Receiver malfunction does occur once in a while, and then burial. During high flow events, we also have receivers that become completely buried in sediment and no longer function correctly. And also receivers are moved from year to year. We've tried to minimize this. We have a group called the ITAG group, and we have what we call a core array. So we essentially have some sites that we are trying to keep steady through the years to be able to compare survival estimates from year to year. But that hasn't always been the case. And there are still examples of receivers getting moved or removed, which make them, no longer available for multi-year analyses. And so, yeah, problem number one is, for these reasons, it is difficult to select receiver sites that are permanent and consistently perform well across many years, so as to combine many different data sets. And then there's another problem. The problem is that survival also varies as a function of non-spatial drivers. For example, the water year, the source population, the size at release, et cetera, et cetera. There's many more that could be considered. And so if you want to look at the spatial kind of makeup of survival estimates, you should probably factor out some of these release group specific variables so that the annual or the study specific survival estimates are comparable. And so, one solution that's often used in statistics is to include like a random effect of release group or study year. But the problem there is a lot of the main software that people use to estimate survival is called Program Mark or RMark, which is the R version of the software, which employs a Cormack-Jolly-Seberg mark recapture model. And currently there's no option for including random effects in that software. So we've kind of been stuck, I think, for those two main reasons, to kind of synthesize the whole 13-year span. I think I've come up with at least one quick solution to better visualize these multi-year data sets. And so I'm going to walk a little bit through how I did that. So here's just survival estimates for a randomly selected release group. So this is a 2022 Seasonal Survival Project release group 4. So the fourth release group of that study. On the x-axis, we have reach number starting from the first reach it encounters, the fish encounter, all the way down to essentially the last reach before entrance to the ocean. And then on the y-axis, we have survival per 10 kilometers. So each one of these reaches, the survival estimate has been standardized to the length of the reach. And we see that survival jumps around through the river, but then we also can take kind of a mean survival. So if we look at how many fish made it to the ocean and then turn that into a per 10 kilometer survival estimate, we can kind of see what's essentially a mean survival per 10 kilometers through the whole outmigration. So in this figure, that's the red line. And what we can do is we can look at, and this is almost kind of like thinking of residuals, but not quite. We can look at how the survival in each reach differs from that mean survival, if it increases or decreases from that mean survival. So this is potentially just a quick workaround for problem 2 that I mentioned earlier. And then problem 1 is also a tricky one, but I wanted to demonstrate a potential solution there too. So this is kind of just hypothetical examples. We have a study on the top which had the red receiver sites. So in between those red receiver sites are the reaches. And I've put just some hypothetical survivals on that top figure for each one of the 4 reaches. And then on the bottom, we have the survival for the green locations. And we can see that the green and the red receiver locations are not the same. And so these reach survivals are not really comparable. They're not apples to apples. But what we can do, and yeah, here's using that same metric again of change over the mean survival. So for example, for the top study, the first reach we see is that survival is 76% of that mean survival, or the second reach is 103% of that mean survival. But what we can do to address that problem is we kind of like flip the script, and we can essentially break the river up into small segments. So here, just in this example, let's say we've broken the river up into 1 kilometer segments. And for each 1 kilometer segment, we can look at the survival rate of the receivers that encompass that segment. So for this black dot here, it falls within the reach 1 for the top release group, and it falls also within reach 1 for the bottom release group. And then we can essentially, you know, we can either rank or take some summary information from the different studies that constitute the survival estimates for that reach. So in this example, there's only 2 studies. And so a median is not super helpful, but we could take the median change in survival for those 2 studies and associate it to that point. And then to further demonstrate what I'm talking about here, let's pick another hypothetical 1 kilometer segment. And in this one, the 1 kilometer segment falls in reach 1 for the first release group, but it actually falls within reach 2 for the second release group. And that in this design shouldn't be a problem. So we can still associate the relevant survival rates from the relevant reaches, and then take some summary statistics such as median or mean and associate it to that point. So that's, I think, a workaround for problem 1 that I mentioned earlier. And so just to reiterate, kind of the metric that I'm settling on for today's talk is, in this example, for river kilometer 13, when comparing reach survival to mean survival across all release groups, survival is on median 87% lower than mean survival. And I use median here because I think it has some advantages over mean, such as if the median is below 100%, in this example 87%, that means that the majority of the release groups had survival lower than the mean for that reach. And that's kind of a nice feature. So a quick disclaimer, the results I'm going to show you are not the results of an analysis in the classic sense. What I'm presenting is a quick and easy way to synthesize and visualize a bunch of publicly available survival estimates. So I'm actually going to present the synthesis of 76 unique release groups released over 13 years in the Sacramento Basin. And these survival estimates are all available on the Shiny app that we've developed. So you can use the QR code, you can use the link, and you can download cumulative survival rates as well as reach-specific survival rates, as well as delta routing survival rates from Russ Perry's team from that Shiny app. Okay, so jumping into it. So this is kind of the meat and potatoes. I'm going to take some time to explain it. On the x-axis, we have river kilometers upstream from the Golden Gate. So 0 is entrance to the ocean, and on the left side of the x-axis, that's essentially the furthest upstream that we release fish, which would be about Redding. And then on the y-axis, we have that same metric I mentioned earlier, which is the median of all of the reach survival over overall survival. So the change in reach survival over overall survival, and then take the median of all of those studies and then do that kilometer by kilometer. And so for this synthesis, I used about 20,000 fish spanning the years 2012 to 2024. And so this is essentially the layout. And, you know, just so people know, I've tried this with mean, I've tried this with ranking and other estimates, and the patterns are the same. The values change a little bit, but the patterns are consistent. And so I'm going to put some geographic kind of markers on there so people can better understand what we're looking at. So we have some estimates in the Redding area, and what we see is the highest survival rates in the system happen to be up there, up until about the Clear Creek confluence. And then we kind of have this part of the river that has still fairly high, you know, relatively high survival rates from about Clear Creek confluence to Vina. And then we kind of have this middle region of the Sacramento, which seems to be the worst in the river part of the system, going from Vina to Colusa. And then after Colusa, survival tends to kind of generally be better all the way to Freeport. And then from Freeport to Chips, we have the Delta, which is, I guess, no big surprise, has essentially the lowest survival in the system. And then the Bay is kind of this intermediate / low survival for, so Chips to the Golden Gate is going to be Suisun Bay, San Francisco, and San Pablo Bays. So that's kind of the general layout that we see. And then we can kind of break this up in different ways. So we can also try to view.
Sorry, Cyril. I'm just
Yep.
going to jump in 5 minutes.
Okay, sounds good.
Your talk authority. Okay, thanks.
Yep, we can kind of look at the breakdown per month. And so here I have December on the top, January in the middle, February on the bottom. We do release fish in November, but there were so few fish released over that 13-year time span that I didn't include November. I also did not include June for the same reason. But we can kind of see that the makeup of where survival is better or worse does change a little bit. We do see kind of a consistent area in that middle Sacramento that can be poor. We also see the Delta here is quite poor. Oh, I should put these overlays again. Here we go. So that Vina to Colusa is still typically the worst place in the Sacramento in those months. And then depending on the month, the Delta can be horrendous or just kind of mean. So in December, it can be quite bad, but in February, it's actually not the worst place to be. And the y-axes on these are the same for these three plots. So that's why the February points aren't quite as spread vertically as some of the other plots. And then same thing for March, April, May. We see some patterns again where that middle Sacramento can be quite poor, especially in March and May. And then again, the Delta can be bad. March tends to be okay. So, take home is February and March. The Delta isn't quite a terrible place to be, but come April and May, it can be quite poor again. And then I just wanted to quickly walk through just a couple of places to focus on where survival is pretty consistently poor. We have going from upstream to downstream, we have a first one here, which is essentially a reach that starts at GCID and ends at Irvine Finch. It's about a 10-kilometer section. And this has usually the highest decrease in survival over mean survival for the river section. And this is especially true in December, January, March, and May. And then we have another portion of the river, which tends to be more around the Colusa area. So kind of highlighting it there. This is a longer section of river. So it starts at about Butte City. It ends at about Colusa. And this also has pretty low survival rates using the statistic I used, especially for the months of April and May. And then finally, there's the Delta. So we have the Delta kind of spanning from Hood to Chips Island in this analysis. And we see that survival is the worst there in the months of December, January, as well as in April and May, which are typically the months when we have slightly lower flows, December, April, and May especially. So it could be that there's a strong flow survival relationship there. I also did this by water year. The information is a little harder to digest perhaps, but we do see generally the same trends. These y-axes are again the same among these four plots, so that's why the wet year doesn't vary as much, because typically in wet years we have better survival. But we do see the Delta can be quite poor and critically dry in dry years. And also the middle river can be fairly poor and critically dry in dry years. So I'll end it there. The support for generating these survival estimates and for developing the Shiny app where they're hosted is from the U.S. Bureau of Reclamation. And I'll take any questions.
So Ryan, I'm going to hand things over to you, and then I think you're going to hand things over to Mike, and then we will take questions on both talks. So Ryan, whenever you're ready.
Okay, sounds good. All right. Can everyone see the presentation?
Looks good to me.
Okay. Well, I'm Ryan Rebnek with California Department of Fish and Wildlife out of the northern region, and I'm going to give a really brief population update and monitoring update for spring run Chinook salmon in Mill and Deer Creek, and kind of talk about some of the issues facing those populations in the last couple years specifically. So, brief overview. Most people are pretty familiar. I'm sick of hearing about it, but Mill Deer Creek are two of the kind of last remaining independent populations of spring run Chinook salmon in the Central Valley, along with Butte Creek, that kind of comprise what we'd call core one genetic lineages of wild spring run Chinook salmon, and some other independent populations that still persist in the Central Valley. So they are listed threatened federally and state, and over the last since 2009, essentially, they've seen a kind of a steady population decline in both populations. And over the last 10 years, that decline has gotten more significant, and they've maintained a low, variable, but low population for the last 10 years, essentially since the 14-15 drought. So, looking at trends and population, here's spawner escapement numbers for Mill and Deer Creek for the last 10 years. You can see it's been sustained, variable, but low during that time. And then in 2023, these populations suffered a cohort failure where we had 16 fish return to Deer Creek and 34 returned to Mill. Followed up with monitoring results from this year, 2024 indicated that they suffered a second consecutive cohort failure, where we estimated 33 fish in Deer and 18 fish in Mill. Add to their woes during the summer of 2024, which was after our monitoring indicated the springer populations had entered into the watershed and into their holding habitat. Park fires started in late July and burned 430,000 acres, and in doing so, consumed about nearly 100% of the spring run holding and spawning habitat in Mill Creek and roughly 70% of the holding and spawning habitat accessible to spring run in Deer Creek. You can see the map that was put together by one of our staff that shows a combination of the footprint of the fire perimeter, as well as the Mill and Deer Creek watersheds. And the colored portion shows burn severity within the, Mill Creek and Deer Creek watersheds. You can see there's a really couple of sections of moderate to high severity burn, specifically in Upper Mill Creek, which was tragically some of the most pristine habitat in both those watersheds up until this point. Oddly enough, one of the things we did notice was we conducted periodic snorkel surveys of Upper Deer Creek, the furthest upstream extent of the holding habitat, and we observed, a low number of adult spring run early in the summer, and then post fire, quite a few more fish had entered that area. So, ultimately, 24 of 33 fish we did count in Deer Creek ended up spawning above the fire perimeter. So, and there's a picture just snapped from the car window when driving around. I think that's the Upper Antelope Creek watershed in that vicinity. Shows the severity of the burn. Then to add to more woes, we had a couple back-to-back moderate to severe atmospheric river events that kind of focused on the park fire burn scar in late 2024 and one in early 25 resulted in some high flow events and peak flows in Deer Creek reaching 17,500 CFS and 15,000 in Mill. And then, of course, coupled with all the things you'd expect from a severe burn scar, so, large debris flows, water quality issues associated with, acute ash runoff and sedimentation, things like that. That all seemed to hit in December and February in both those creeks, which was pretty concerning for the fish in the streams and the eggs in the gravel, and it wasn't great for monitoring either. So rotary screw trapping, despite technical difficulties associated with big flow events full of trees, we still have not detected any brood year 24 Chinook salmon in Mill Creek. So specifically, young of the year from spring run or fall run have not been caught yet. And we've only encountered 6 juveniles from deer. Like I mentioned before, we had a number of the spring run all spawn upstream of the fire, so we're hopeful that they were not impacted so much. But time will tell as we continue to monitor. So, emergency conservation actions. I'm just going to touch briefly on this because Mike's presentation is going to go in a lot more detail. But in 2023, after the first cohort collapse of Mill Deer Butte, fish agencies, CDFW, U.S. Fish and Wildlife Service, and NIMS and others kind of jumped together and initiated some emergency actions, one of which was the immediate collection of juvenile Chinook from Mill, Deer, Butte, as well as Battle and Clear Creeks to establish a captive broodstock population. So young of the year juveniles were collected in rotary screw traps on Mill and Butte, Battle and Clear, and then yearling Chinook spring run from Deer Creek were captured from various methods of active capture methods, mostly like snorkel seining, where people dove down underwater with seine nets and tried to drag the bottom of these deep pools and collect fish. Ultimately, a target of 500 fish per population was captured. I think right now there's, as of typing this at least, there's 300 fish from Mill, about 250 from Butte, about 100 from Deer, and a handful from Battle and Clear that were transferred to University of California, Davis, Center for Aquatic Biology and Aquaculture, which were really helpful in developing a immediate holding facility where they could quarantine these fish from the wild, rear them, treat them for all the different pathogens, and then get genetic samples and help from CDFW and NOAA geneticists to try to develop, lineages, family relationships, and ultimately hope to develop spawn matrices where we can kind of evaluate what kind of potential captive spawning options these fish are going to have. Ultimately, this is a emergency action to try to preserve the genetic lineages of these groups in the hopefully unlikely event of a third cohort failure. In addition to that action, U.S. Fish and Wildlife Service and staff from Livingston Stone jumped in to help as well. They were able to hold and spawn spring run at Livingston Stone that were captured in winter run broodstock collection, transfer eggs to CDFW, to help us kickstart our potential in-stream supplementation or reintroduction plans that we may implement in the future. So, but that's kind of about to be what Mike's talking about. So that's kind of all I have for spring run updates. If anyone's got questions for me, you could probably tackle them after Mike's presentations, my guess, or you can reach out to me directly too outside of this.
All right, thanks, Ryan. Yeah, Mike, whenever you are ready, go for it.
All right, hi everybody. It's Mike Mimio, Region 1. I work with Ryan. I'm going to get this started here. Can everybody see the slides?
Yep, looks good.
Okay, I'm going to be talking about the spring run Chinook salmon emergency egg incubation action on Clear Creek that Ryan was talking about. It was conducted by our folks up here, CDFW, in cooperation with Livingston Stone, U.S. Fish and Wildlife Service, BLM, and Bureau of Reclamation. See if this works. Get on the right screen. So just to go a little kind of reiterate what Ryan said, reason for the action, 2023-24 spring run cohort collapse. He basically explained how this, why we needed to have these actions. So propagation of captive broodstock at UC Davis, Caba, and our egg incubation box implementation on Clear Creek. It was a pretty quick emergency action, quick moving, fast moving. CDFW submitted an NOE. It's on Sequanet for this action on 10/8. You'll see how quick that was. So a little more background into Livingston Stone. Conservation hatchery built specifically to enhance winter run Chinook salmon, as Doug touched on. They produce 200,000 to 800,000 winter run juveniles annually. As he said, broodstock are captured in the Keswick trap. Incidentally, they also capture spring run every year. Usually those spring run are returned, those adults are returned to the Sacramento River to spawn, and just after they get a FOI tag. In 2022, adults were taken to Clear Creek to spawn as part of a drought emergency action, but observed limited spawning success. So beginning in 2024, the department requested up to 40 trapped spring run to be retained and spawned at Livingston Stone. So in 2024, June, July, July, a total of 11 spring run adults were captured at the trap. Genetic analysis showed that all the adults were of Feather River hatchery origin, so not Core 1 fish, even though they were unclipped. September 26th, 3 of the unmarked females were spawned with 3 unmarked males, and eggs were incubated until the eyed stage at Livingston Stone. So the objective of this study, or this action, was to enhance Clear Creek. The decision was made to put those eggs into Clear Creek. So to enhance Clear Creek spring run population and to analyze the feasibility of this new technology hatch partner boxes for future salmon population enhancement efforts on places like Mill and Deer and other, as well as others. CDFW, we got these hatch partner boxes. Actually, if you guys don't mind, I'm turning on my camera real quick, kind of give you guys an idea what they look like. So that's the bottom. They are vented for flow through. That's a little window. Kind of hard to see it, but it gives you kind of a scale how big these things are. CDFW Region 2 actually were made aware of this new incubation technology being implemented in Idaho. They did a lot of the legwork. They found the patent, reached out to the inventors, and were put in touch with the Shoshone-Bannock tribe, who had been implementing these boxes on the Salmon River to enhance their Chinook populations. They began a collaborative effort to implement and share data as part of their North Yuba spring run reintroduction program. They purchased 20 hatch partner boxes from Partner Steel Company Incorporated, who actually their main business is building and fabricating barbecues, but they worked with the Shoshone-Bannock to design and fabricate these boxes. Due to some funding constraints, Region 2 was unable to use the boxes, and they had presented these boxes to us previously as part of a training, and we jumped at the chance to borrow a few of them to be implemented on Clear Creek as part of this emergency action. So, how am I on time? Am I good?
Yeah, we got
Okay.
about 4 or 5 minutes until we want to move to Q&A. So yeah,
Okay.
all good.
So I'll speed up here. 3 hatch partner boxes were installed in Clear Creek near the Horsetown Preserve. They're anchored to the substrate using 1 to 2 foot steel spikes with a little washer welded to the top. We put them through the handles and piled rocks along the apron, the metal apron. A total of 11,909 eggs were split into the 3 boxes. And you can see one was just about 5,000, 4,300, and 2,600. Those number of eggs corresponded with the number that was counted at Livingston Stone. We wanted to keep it that way so that we had an accurate starting egg count for egg to fry survival. So it's got a little bit better idea of where we put the boxes. We put them on the far bank from the BLM property to try to avoid detection by people that frequent that area. So following installation, all the boxes were checked 3 times a week when possible, and dead eggs and alevins were removed from the internal egg box. They have an internal egg box that holds inside there. Water quality metrics were also collected, pH, temperature, dissolved oxygen, and water depths and velocities directly adjacent to the hatch partner boxes were also collected at least weekly. Alevins observed within all 3 boxes for the first time on the 9th. So 10 days after we installed, they hatched. This is a little video I can share. They have a cool little viewing window. We can watch the eggs and see them hatch and kind of get an idea how many were if there was a problem with mortality. So Ryan kind of touched on our rough winter this year. We had the bomb cyclone atmospheric river that hit November 18th through the 20th. We decided to leash the boxes prior to the storm and try to protect them. We didn't know how they would hold up to a high flow event yet. They're brand new to us, so put a little rock wall around them to try to avoid high velocities going over the boxes. Clear Creek is protected by Whiskeytown Dam, but flows did peak at 1,970 CFS, and the boxes survived. Just a little bit of sedimentation inside the egg boxes was removed, and very gently, because they're it's a very critical, fragile stage of development for these fish. That was one thing I do want to touch on, is we really didn't want to disturb these boxes once the eggs started hatching, just to avoid inadvertent mortality. So then we released them. After monitoring closely, we released the fish December 6th and 9th. So you can see a total overall survival was 93.79%. So pretty good for our first trial. Total days from spawn was only 74 days. Pretty warm temperatures in Clear Creek. So maybe a little bit early that we released them, but we also had another storm coming in. Our cumulative temperature units were in the 1400 range at time of release. But we wanted to get them out ahead of a large flow event, predicted large flow event. So that's the reason why we chose that. We didn't know if we'd be able to get into them, because these boxes, the fish cannot leave volitionally. So it was either get them out at that time or wait another week or 2, and to avoid mortality of the fish not being able to feed, we wanted to just get them out. So average water velocity, this is just kind of more statistics. It's basically, we kind of tried to hone in on the water velocity around the boxes for future reference. 0.85 to 1 foot per second seemed to work. That was what we had, but the 1 foot per second seemed to work. We didn't get to spread these things out due to the emergency nature of this project. I would have liked to have done a little more experimentation, but given the low numbers of eggs in boxes and the fact that they were spring run and their dwindling numbers, we wanted to kind of err on the side of caution. So like I said, egg to fry survival for this was 93.8%. Just a little comparisons for context. Egg to fry survival from the RSI on the McCloud River in 2023 is 94, so we're right on there. And then just from a Feather River hatchery report, eyed egg to fry survival is around 88.5% in 2023. Lessons learned, because it was such a small sample size, it's really difficult to draw any real conclusions. Only 3 boxes. Egg density may play an important role, as survival was inversely related to density. So actually the Shoshone have done a little bit more work on this, but they said in their studies they showed that survival decreases after you get more than 5,000 eggs in the boxes. We didn't get that high, but it seemed like it was the lowest density had a lower survival, but not much. So just thinking that maybe they just have more room to roll around and maybe impact the eggs and the alevins. And then the boxes are surprisingly resilient to high flow events, at least in places like Clear Creek where it's dam controlled. And then acknowledgements. Thank you to all the cooperating agencies. Special thanks to Livingston Stone. They already, actually, an update on this, they already have captured one spring run, one fish that came back as an adult spring run as of this week, and they're holding it for us for our next year of this project. So, and I think there are projects moving or plans to move forward with these boxes on places like the McCloud River winter run reintroduction and Klamath River population enhancement. So I hope I'm good. I think I had a couple minutes to spare. So with that, I can show another little video. Hopefully you guys can see this. This is the release day. Apologize for it being upside down, but as you can see, they're swimming away, looking for cover, eating, doing all the things that we want to see juvenile fish doing when you let them go in the creek. So
Awesome. Thanks, Nick. And Ryan. Let's change gears and chat a little bit about Fall Run for our last couple of presenters. So we're going to have Colby and then roll into Brad, and again we'll hold questions until both of them have wrapped up their presentation. So Colby, go for it.
Okay, hi everyone. Are my slides up and ready?
Yep. Yeah,
Okay,
it looks good.
I am Colby House. I am with CDFW's Anadromous Fisheries Conservation and Management Program. And today I'm going to take a bit of a step back and look at the Central Valley as a whole, and talk about Chinook salmon spawning escapement for 2024, as well as past year's trends. And the focus is going to be Sacramento River Fall Run Chinook, but we'll also talk about the San Joaquin Basin, as well as escapement of other runs, winter, spring, and late fall. Okay, so for some quick spatial context, so everyone's very familiar with these tributaries and hatcheries. I just want to touch on the 2 basins in the Central Valley, Sacramento and San Joaquin, and just so that the Central Valley hatcheries produce a lot of Fall Run Chinook, about 32 million annually. So I'm just going to briefly walk through each of those hatcheries and their production. So northernmost hatcheries, Livingston Stone, produces endangered winter run Chinook. And then southeast of there is Coleman National Fish Hatchery on Battle Creek, produces fall and late fall. And then you'll see Upper Sacramento River Basin also includes natural areas. Some important runs include Clear Creek and Battle Creek, which are labeled on the map, with Mill Deer and Butte Creeks also supporting Fall Run. But as we've discussed, those are very critical streams for Or1, Central Valley Spring Run populations. Moving south, we have the Feather River Basin, also includes the Yuba River. Feather River hatchery produces fall and spring Chinook. And the southernmost drainage to the Sacramento River is the American River Basin. So Nimbus Fish Hatchery is located in the American River and produces fall Chinook. And then the southern end of the Central Valley is the San Joaquin Basin, which has 2 hatcheries that produce Fall Run, the McCollum and Merced River hatcheries. Escapement to the San Joaquin Basin also includes tributaries like the Stanislaus and Tuolumne rivers. And then at the very bottom, we have the Salmon Conservation and Research Facility located below Friant Dam on the main stem of the San Joaquin. And this functions to produce spring run Chinook. Okay, so we'll start by talking about Sacramento River fall run Chinook, which I will commonly refer to as just Sac Fall throughout the presentation. So this population is the largest contributor to ocean fisheries. It's also the largest component of the total Central Valley escapement. And importantly, it serves as the indicator stock for the Central Valley Fall Chinook complex. So here we have a graph of adult spawning escapement over the last 20 years. Sac Fall have an escapement goal range of 122,000 to 180,000 adults returning to both hatcheries and natural areas. And so we show this range on the graph in red. And in 2024, Sac Fall adult escapement was 99,274 adults, which is about 23,000 under our minimum escapement goal of 122,000 adults, and falls around 34,000 under last year's escapement of 133,783 adults. So as you can see, in the past 10 years, we've been within or above that upper end of the range in only 3 out of the past 10 years. So here we show the number of adult Sac Fall that returned to hatcheries and natural areas within the Sacramento River Basin over the last 20 years. Hatchery escapement is that light blue portion, and natural area escapement is the dark blue portion, with minimum escapement goal of 120,000 is represented by the red dotted line. And in 2024, about 72,500 Sac Fall adults returned to natural areas to spawn, while about 27,000 adults returned to the 3 Sacramento River Basin hatcheries, so Coleman, Feather, and American. Generally, the proportion of adult natural area escapement exceeds that of hatchery escapement. It's historically between 40 and 93%. And at about 73% natural area spawners, 2024 returns remained above our 20-year average of 67%. So here we have a graph of adult Sac Fall escapement now broken out by major basin over the last 20 years. Okay, can people still hear me? It like froze for a second.
Yeah, I still hear
Okay.
you for now.
You are?
Yeah.
Okay, great.
Yep.
Okay, so upper Sacramento River Basin is in dark blue, Feather River Basin is that middle portion, and American River Basin is that top light blue portion. So at around 50,000 adults, roughly 50% of the basin-wide escapement came from the American River. This is much higher than the long-term average of 21%, and it's largely due to the below average escapement to the upper Sacramento River Basin, which was around 7,000 adults and represented only 7% of the basin-wide escapement. Feather River made up 43% of total basin-wide escapement, estimated at around 42,500 adults, which is similar to the 20-year average of 41%. And so, yeah, in 2024, we saw a major deviation from the 20-year average, where Feather River Basin and Upper Sacramento River Basin typically yield almost equally high portions of adult spawners. But we saw very low contribution by the Upper Sacramento Basin in 2024. So now looking back at total spawning escapement of Sac Fall, this graph looks at Jack and adult return over the last 20 years. Jacks are 2-year-olds, shown in white, whereas adults are ages 3, 4, and 5, shown in blue. In 2024, approximately 99,300 adults and around 19,200 jacks returned to the Sacramento River Basin. This year's jack escapement was the highest since 2019. And for comparison, the highest jack escapement recorded was in 2011, around 86,000 fish. And so monitoring jack escapement is important because we use this information in forecasting the number of fish available for harvest in upcoming fisheries. And very briefly, this is done by fitting the postseason abundance estimate, which is the Sacramento index. It's the sum of ocean harvest, river harvest, and escapement. And we fit this to jack abundance with this autocorrelation correction factor, which just simply adjusts the estimate up or down based on model performance from the previous year. And so our jack abundance allows us to forecast the ocean abundance 1 year ahead. Here we take a look at Jack and adult sac wall escapement to each major basin over the last 20 years. Jacks again are in white and adults are in the 3 shades of blue. So starting on the left, overall escapement to the upper Sacramento River Basin was 3rd lowest on record at about 7,000 adults and 8,500 jacks in 2024. This is a 55% jack rate, and this proportion exceeds the 20-year average in the upper Sacramento Basin of 18%. In the Feather River Basin, which includes the Yuba, approximately 42,500 adults and 5,000 jacks returned in 2024. So that's 11% jacks, which is very close to the 20-year average of 14%. And the American River Basin had about 49,700 adults and 5,700 jacks return, which is about 10% jacks. And this is lower than the 20-year average of 18%. And just want to point out that overall in 2024 was the highest escapement to the American River Basin since 2013. So that wraps up our focus on Sacramento River Fall Chinook, and I'm just going to briefly touch on the southern part of the Central Valley and look at fall run escapement to the San Joaquin River over the last 20 years. So we separate out the San Joaquin River Fall Run, not only because it's a different basin, but returns to this basin aren't used in ocean fishery planning, so they don't count towards the Sacramento River Fall Run escapement goal and stock forecast. And so with that said, here we have a graph of adult returns in green with jacks in white. In 2024, approximately 32,300 adults and 10,600 jacks returned to the San Joaquin River Basin, which is the highest total and adult escapement to the San Joaquin River Basin since 2000. Jacks made up roughly 25% of the total run, which is just below the long-term average. Jack contribution of 29% for this basin. So here we have adult and jack escapement to the 4 main San Joaquin River tributaries over the last 10 years. Jacks again are in white, adults are in varying shades of green. And the McCollum River is generally the largest contributor to San Joaquin River Basin escapement. And in 2024, we saw a total escapement of about 35,400 fish, which increased from last year's escapement of around 28,700 fish. And so 2024 was the highest escapement to the McCollum River on record, with 2023 being the second highest. And so compared to 2023, the Merced River saw a substantial decrease in escapement, whereas the Stanislaus saw a slight increase in returning adults, and the Tuolumne River had its highest escapement since 2013. But compared to the McCollum, the adult returns on the Merced, Stanislaus, and Tuolumne are relatively low. And so before wrapping up, I'll just briefly touch on the other runs returning to the Central Valley in 2024. Here we have a graph showing escapement of late fall in orange, endangered winter run in purple, and threatened spring run in green on the right, and all jack counts are depicted in white. The late fall run returns totaled about 4,200 adults and 100 jacks, which is a slight increase from 2023, but it continues to follow this declining trajectory for the stock. And winter run returns totaled about 800 adults, 600 jacks, which is extremely low. And spring run returns were also very low, 2,500 adults and 200 jacks. And it's important to note that spring run natural area surveys report a combined jack and adult escapement estimate, whereas jacks are reported separately from adults on the Feather River hatchery. And so this total estimate for spring run is largely carried by the Feather River. Spring run returns to natural areas were very low, as we discussed earlier today. And with that, thank you for your attention, and I will pass it off to Brad.
Thanks, Colby.
All right. Thanks, Colby. Let me get this going here. Come on. All right, so I imagine everybody's getting tired. You'll be happy to know that this is a short presentation that I have. Just kind of wanted to get some wheels turning, maybe about some different ways to look at the data that we sometimes don't talk about. So this idea came up in kind of early discussions for this meeting, and knowing that the Sacramento River main stem fall run have been a concern. They're not doing very well. I'd suggested that we take a look at the spawner recruitment data. So we know how many fish adults are spawning upstream of Red Bluff Diversion Dam, Battle Creek, Clear Creek, the main stem Sacramento River. And then we have an estimate of how many juveniles come out. And so I suggested we look at those two things together. And I started putting the data together, and then Colby and I were having some correspondence, and I was reminded in that I saw that Will Satterthwaite had done basically the exact same thing that I was planning to do as part of the Pacific Fisheries Management Council. It had convened a team to look at the Sacramento Index. So I reached out to Will and he got his permission to share his results that he did. And this is from a report that he did, very drafty report. Here's the title of it. You could see it's not peer reviewed. It's for discussion purposes only. And that goes for my presentation too. But I wanted to make sure to credit Will's work here. So what I did is I took Will's figures and kind of made a few modifications in terms of adding data for more recent years, just to kind of illustrate the point. So just to get you oriented here. So again, these are figures from Will's draft write-up. The difference between these two is the one on the left is looking at 2002 through 2020, and the one on the right is excluding 2002. So if folks remember, 2002 was kind of an odd year in that there was a massive recruitment of adults, spawning adults to Battle Creek. I think there was close to 400,000 fish that year. And of course, he's plotting the number of females in the upper Sacramento Basin. So anything upstream of Red Bluff Diversion Dam that we have data on. And so when you include that 2002 data, it does give you a really different result. And it's kind of suspect just because of so much of that number is driven by the high number of fish that came back to Battle Creek in that year, which certainly, far outstripped the capacity of that stream and is well beyond what you would ever get in a stream like that without the hatchery on it. So in the next figure I'm going to show you here, I'm working with this excluding 2002 data, and I'll get to that in a second. So you can see also that Will went ahead and fit a Ricker curve to these data. That's what the blue line here is. You could pretty reasonably argue that we may not have the data to support a Ricker curve. You could argue that there should be, this is kind of a more of a linear relationship. That's entirely fair. And then also there's a flow covariate that was included. And so this sort of reflects the change in production that you would get with the one standard deviation higher or lower flow from the average. And there's some caveats to all that, but I just wanted to orient you to the data that I wanted to show you. Then, whoops. So then what I did is, so using, again, working with that plot that is excluding 2002, I added labels for all the brood years, and you can see that in this figure. I added in 21, 22, and 23 with data I pulled from SACPAS for fall run juvenile production. Now there's definitely some limitations to that because those data do not reflect, they're very preliminary. They don't reflect some of the modifications that U.S. Fish and Wildlife Service is going to do to those to account for, to actually make them true fry equivalents and remove any hatchery fish that might have been included and things like that. But I wanted to throw them in here just to kind of illustrate how this works and let people see kind of where the data lie, kind of interesting patterns that I don't necessarily want to get into today, but I mean, we could probably spend an hour talking about this figure and kind of tracing bird years and patterns of juvenile production from different levels of spawners. But you can definitely see there is a pattern where, as you would expect, the number of juveniles you get is strongly influenced by the number of adults that are spawning upstream. We are seeing some kind of interesting patterns. There are some points that are falling well below that line, like 2014 and 2021. This suggests something was maybe off in those years. And then we have some other, observations that are really high. 2013 is quite high above the curve. So, don't know if that's something that's meaningful or not. Obviously, there is a lot of uncertainty with our juvenile production estimates, particularly for fall run. They don't get as much of the sort of the monitoring effort as do winter run. But still, this seems like pretty interesting data to me to look at and try to understand what's happening with Sacramento River fall run on the main stem and from Battle and Clear Creek. So I mentioned a couple of these caveats. Another few that Will brought up that I want to pass along is that we really don't have many observations for high abundance. We have that one data point hanging out there from 2003. That ties into the sort of the uncertainty about whether this rigor relationship is appropriate. And we also don't really have a lot of high flow conditions. And we have some kind of an unbalanced observations in terms of high flows with high spawners and things like that. So there's definitely some issues with the data. We'd like to have more observations. And again, the flow covariate is definitely preliminary. Will didn't put a lot of effort into that. He kind of characterized it as having kind of a weak influence on changing the relationship. And it probably would be worth taking a closer look at that. But hopefully folks can see this is kind of a nice way to look at the information that we're getting out there. Earlier in the session today, listening to some of the other talks, I was reminded, that maybe the reason that we don't talk a lot about the spawning recruit relationships is that we tend to talk about egg to fry a lot on the Sacramento River. So I threw this together earlier this morning, but if you take these exact same data, and for simplicity of this example, I just assumed, okay, let's assume there's 5,000 eggs per female in every year. Exact same data, you can turn this into an egg to fry figure, you get what I'm showing here on the right, which, it's useful, but I feel like this is more useful helping you understand kind of patterns of what's going on out in the system. And I'm not sure that having fecundity, which is not something we have a tremendous confidence in, typically that comes from a subsample of fish that are spawned at the local hatchery. It's not as though we know exactly how many eggs were, there for all the females that were spawning naturally in river. So that's just something to think about. So takeaways, the spawner recruit analysis I think is pretty useful. It integrates the adult and the juvenile data, allows a basis for some visual interpretation, and then with whatever your relationship you want to fit between the two, whether it's Ricker or something else, provides a basis for looking at covariates. One challenge for Red Bluff Diversion Dam data is that it's going to be capturing juveniles that are coming from all these different places and some other smaller streams. So it's not necessarily, we don't know how each of these different areas are contributing, and it likely varies from year to year. Maybe in some years we do get a lot of juveniles coming in from Battle Creek just because it's so close to Red Bluff Diversion Dam. So that is kind of an area of uncertainty. And then sort of the next steps would be, this is useful data now. What might we do to make it more valuable in the future for helping us manage fall run and tracking the production? That could include a lot of different things, maybe more formally accounting for the monitoring data that's happening already at Clear Creek, for example. It could include genetic parentage analysis to try and attribute the juveniles that we see to the different source populations of spawners. We heard a little bit about changes that are happening to efficiency modeling at Red Bluff Diversion Dam. That would certainly be very complementary to this. So again, just trying to get folks thinking about this stuff. I think we have some really good information here and probably could use it to better effect going forward, especially with a few modifications. So thanks.
All right, thanks so much, Brad. All right, I'm gonna aim to let everybody go at noon as promised. We do have some time for questions for Colby or Brad if anybody has anything. I want to give a huge thank you to all of our presenters. Really appreciate all of you sharing all of your wonderful information. Thanks to all of you for joining and your great questions. Like we said, we're going to post the recordings for the presentations as well as the slides. Presenters, please don't forget to send this stuff over on the SRSP's website soon. And with that, I hope everyone has a really wonderful rainy or snowy but restful weekend here. So take care all, and we'll see you next
Thanks.
time.
Thanks.
Thanks, everybody.
Bye, Beth.
Thanks, Mary
Bye.
Beth.
Thank you.
Bye.
Bye, all.
Ciao, Bo.
Thank you.